Welcome back. Please take your seats. Our first speaker this afternoon will be Noel Swanson, joining us from the University of Delaware, and he's going to talk about CPT, spin statistics, and state-space geometry.
Great, thanks, Mike. So the theme for today is supposed to be what are the characteristically relativistic features of quantum field theory. Two of the sort of foundational theorems that we find in relativistic quantum field theory that on most tellings are the kind of paradigm examples of the sorts of things that are characteristic of relativistic QFT are the following. The Cpt theorem tells us that any well-behaved relativistic QFT is going to be invariant under a general reflection symmetry that reverses the direction of time, flips right and left-handedness, and conjugates all the charges present in the theory. There's another theorem, the spin statistics theorem, that says in any well-behaved relativistic QFT, fermions always have half-integer spin and bosons have integer spin. So this is a theorem linking spin properties of particles or quanta to their statistical behavior. And one of the things that's interesting is that when you look at non-relativistic quantum theories, these theorems don't have to hold. And so they look like the kinds of things that arise when you move to a relativistic quantum theory. There's interesting open questions about whether or not they fail in classical relativistic theories that we might get a chance to talk about at some point. The main question I'm going to be interested in today is this sort of chicken and egg problem. Which of these two theorems comes first? When you look at the proofs of the Cpt theorem or the spin statistics theorem, they tend to have a lot of assumptions in common. In many cases, the Cpt theorem gets used as a lemma to prove spin statistics or vice versa. So they seem to be intimately related, but at first glance, it's not at all obvious how that's the case. It's not even clear that the well-behaved thing in scare quotes is the same in these instances. So there's an interesting explanatory project here, which is, does one explain the other? Or maybe the answer is neither. They have a kind of underlying common explanation coming from relativistic QFT. There's some other interesting adjacent philosophical questions here. First one is just what explains these two things? We don't actually have a perfect grip on the explanations for either by themselves. Part of the problem here is that you've got proofs of both theorems in different frameworks for quantum field theory, and they have overlapping and similar assumptions, but they're different. So just figuring out how to sort of patch together this sort of set of different frameworks is interesting. Related to this issue, in Jonathan Bain's recent book on the CPT and spin statistics connection, he issues a kind of skeptical challenge. He says that when you look at proofs of these theorems in different frameworks, they don't have enough in common that we can confidently say at this stage we have something like a convergent explanation towards why these things hold. There's too much divergence between the different proofs. Here's another interesting philosophical question. When you look at the Cpt theorem, it seems to be saying something like, no matter what the laws of your relativistic quantum field theory are, they can't pick out a preferred direction of time independently of picking out a preferred notion of space and a preferred notion of charge. Somehow there's a necessary connection between these different kinds of orientation structures. And Hilary Greaves asks, why is there this kind of necessary connection between what, again, appear to be completely distinct orientation structures, temporal orientation, spatial orientation, and a kind of charge orientation. You might ask questions about whether or not, say, the Cpt theorem is really quantum mechanical. Hilary Greaves argues that there's a kind of analog of the Cpt theorem in relativistic field, classical relativistic field theories. You might also ask questions about whether the spin statistics connection is really relativistic. Sudarshan has a kind of interesting proof that looks like it eschews relativistic assumptions. And then most of the theorems work in 4 dimensions in Minkowski spacetime, and there's all sorts of questions about how to generalize this to lower dimensions in curved spacetime and what this means for effective QFTs. Most of the theorems also keep quantum field theories with massless particles at arm's distance, and so we may talk about some of these complications as well. Okay, so for the talk, I'm going to focus on proofs of the Cpt and spin statistics theorem in the framework of algebraic quantum field theory. So we've got some really interesting mathematical theorems here, but the sort of physical understanding behind them is really sketchy. And part of the reason why it's sketchy is that the theorems tend to start at a very kind of late stage of the game. And so one of the things I want to do is sort of start from the very beginning and go back to the kind of the axioms, the Hogg-Kossler axioms that help carve out the framework that is algebraic quantum field theory. So at least the way I'm going to tell the story, both theorems start with a net of C-star algebras, right? So these are isomorphic to the algebra of bounded observable, or sorry, a subalgebra of bounded observables on some Hilbert space. But at the start, we don't choose any Hilbert spaces. It's just a collection of elements that have algebraic properties. We assign those to various space-time regions. And then we require that this assignment of algebras to regions obey the following set of axioms. The first, isotony, says that if I've got one region that's nested in a bigger region, this is a subalgebra of the algebra assigned to the bigger region. Microcausality says that the observables localized in space-like separated regions will commute. Covariance tells me that there's a representation of the relevant space-time symmetries acting as net automorphisms. So in this case, that'll be the, this is actually kind of important. So in this case, what the covariance axiom usually says is there's a representation of the connected Poincare transformations. So translations, boosts, and rotations, but no reflection symmetries yet. Then you stipulate that there's at least one translation invariant state, which is a sort of necessary condition for interpreting it as a vacuum. And then in the vacuum representation, or representations plural, you require the spectrum condition to hold, which is to say that the unitary operators that generate the translations in that representation have spectral support in the same light cone lobe and momentum space. So this came up in Wayne's talk earlier today. This is going to ensure that the energy is positive in any Lorentz frame in the theory. Okay, so that's the sort of the basic starting assumptions. Anything that's going to count as a model of AQFT when I talk about it is going to satisfy those 5 axioms. I should say one thing I realize I glossed over pretty fast. So you start with these abstract algebras. What's a state in this case? A state's going to be a kind of normalized positive linear functional on this algebra that assigns a complex number to each element of the algebra. You can interpret that number as the expectation value of the associated observable. Then if I give you a state in this sense, I can then generate a Hilbert space representation of the algebra as a subalgebra of operators acting on a Hilbert space. And the state, the linear functional, is going to be represented by a vector in that GNS representation. So when I specify a model of AQFT, we start with this net of algebras. Typically, not all of the states on this net are going to be physically realistic. We have to set some sort of realistic boundary conditions, and that's a really important sort of physical input to the theory. So for the purposes of doing or studying the Cpt and spin statistics theorem, we're going to require that the set of physically possible states satisfy a particular kind of boundary condition that I'll explain in a second, called the DHR-BF selection criteria. These are loosely going to characterize global states that have the same charge boundary conditions. And then we're going to end up using a whole bunch of technical auxiliary assumptions at various states, at various places. I'll introduce these as we go along. At this stage, the important idea is that we can't, at this stage, we can't get the Cpt and spin statistics theorem just from 1 and 2. We've got to add some additional stuff. And the project of figuring out how these theorems are interrelated is going to boil down to a lot of figuring out, which of these assumptions are weaker and stronger and how they're interrelated. Can they be proven from other things? That sort of thing. As far as a broad theme, one thing that we're going to see is, in addition to the standard assumptions, we're pretty much always going to need some kind of additivity. So weak additivity gets used a lot. Basically, what that says is you can take the algebra, usually in some privileged representation, you can take the algebra associated with some region, translate it using the translations, and then generate an algebra that's equivalent to the global algebra in that representation. There's going to be a lot of analytic continuation arguments, and some of the analytic continuation arguments you get for free from the axioms we have, but there are going to be a few key places where you need to add a few more analyticity assumptions. So in particular, we're going to need additional analyticity to prove something called wedge duality, as well as something called the Biesian-Wickman property that I'll talk about in a second. And then the last thing that's kind of important is that this last thing listed here, the distal split property, or the split property in general, is a kind of thermodynamic well-behavedness assumption that we'll talk about. That seems to be a kind of crucial ingredient in both proofs. So what I want to do is I want to start by just flagging a couple of the main kind of technical ideas that appear in both proofs that might be a bit more unfamiliar to people. And then I'm going to sort of walk through, starting from the Hogg-Hassler axioms, and give a kind of story about how you get the Cpt theorem. And I'll try to do my best to sort of physically motivate each stage of the process, which is something that I think is missing in a lot of technical discussions of this stuff. And then the third part of the talk, I'm going to, from that sort of vantage point, then kind of look over at the spin statistics theorem and see how you can fit the spin statistics theorem into that picture. So one of the technical properties that you end up proving en route to both theorems are these duality properties, right? So microcausality is this assumption that space-like separated observables commute. So in particular, if I look at pick some physical state, go to that Hilbert space representation, I can generate additional algebraic quantities in that representation. Microcausality is going to say that the algebra that I assign to here, O prime, is the space-like complement of region O. So that algebra is going to be a subset of the commutant of the algebra that I assigned O. Fancy way of saying that space-like observables commute. Duality conditions are going to be certain kinds of maximality assumptions that say that these algebras are as big as they possibly can be consistent with microcausality. So this gets turned into an equality for certain special regions. So here are 4 such assumptions. The one that gets most commonly discussed is called Hogg duality, which says that for any double cone region, the algebra assigned to the space-like complement is equal to the commutant. And here's your double cone, right? It's the intersection of the past and future light cone. It's a bounded region. I can also have duality for space-like cones. Same condition, but here the relevant region of these space-like cones. Here's a space-like cone. This is unbounded and extended in some space-like direction. Wedge duality is, again, the same condition for these space-like wedges, which are unbounded along this axis, and they are unbounded in this direction. So you can imagine this sort of wedge region that's nestled into the side of a light cone. That's going to be a very central and important property in what follows. And then the last one is kind of weird and technical, but it's the kind of minimal duality condition you need to get a bunch of talk about charges off the ground. And these are all listed in decreasing strength. So we typically don't expect Hogg duality to hold in general. It's equivalent to the absence of spontaneous symmetry breaking in the vacuum sector. This is a bit weaker. This is a candidate for something that we might think is going to hold in pretty much all models of physical interest. It's certainly an ingredient in all known algebraic proofs of the Cpt theorem. This is a bit weaker. It's entailed by wedge duality. So one motivation for this is, well, if we have wedge duality, we get this for free, and then we're off to the races with being able to describe charges in the theory. Which brings us to, how on earth do we describe charges in the theory? So because we're starting with these algebras, eventually these algebras are going to be interpreted as well, first pass, something like algebras of physical quantities. And these are going to be gauge invariant quantities. And so when you look at most other frameworks for quantum field theory, charges can be created by the action of charge creation operators. But these are field operators, so typically not gauge invariant. And so at this stage, we don't actually obviously have anything like charge creation operators in our formalism. So instead, in the algebraic framework, we tend to model, or at least one of probably the most direct way to model charges are by using certain specialized morphisms that map. This is the quasi-local algebra, so the C-star algebra that's generated by all the local algebras, that map the quasi-local algebra into the algebra of bounded operators on the vacuum Hilbert space. These morphisms are required to be localized, so they act non-trivially in some region may be a double cone, maybe a space-like cone. And they're transportable, namely that you can transport them to other similarly shaped regions using the action of the translations. So the interpretation of these guys is going to be something like this. I take the vacuum state, omega. I combine omega with one of these morphisms, and what I get at the end is a charge state with some charge q that's localized in the region that the morphism is localized in. Here's the first place where these various duality properties come into play. If I've got one of these duality properties, I can prove that these morphisms have nice categorical properties. I can take the set of morphisms, interpret intertwiners between them as arrows, and prove that this thing has got the structure of a symmetric tensor star category, so it's got tensor products, it's got all sorts of lovely structure. If I've got some nice thermodynamic properties, so if the split property or the weaker distal split property holds, I can prove that my category has conjugates. So for each charge morphism, there's some conjugate charge morphism that's defined by this property. If I apply both of them to the vacuum state, I get some state that may not be the vacuum, but it's got some component in the vacuum sector. And when I take unitary equivalence classes of these morphisms, I get what are called charge sectors, which are sectors of states that have the same net global charge. So this is one way that I can describe charge structure in algebraic quantum field theory. There's another way to describe it, and one of the kind of interesting things that happens in DHR BF superselection theory is you show that these two ways of talking are equivalent. So here's another way of talking about charge. I start by imposing a physical restriction on states, right? I say I'm only going to count states as physical that have certain boundary conditions, namely the following. For every physical state, there's some double cone or space-like cone O, such that when I restrict the representation of the quasi-local algebra to the space-like complement of O, that's going to be equivalent to the vacuum state outside of that region. So what are the boundary conditions here? Something like I'm only counting physical states that look like the vacuum outside of some double cone or space-like cone. Now, prima facie, it's not at all obvious why that would be interesting, but first monster theorem, turns out that these representations form a category, and you can prove that they're categorically equivalent to the category of localized transportable morphisms. And so in particular, all that lovely structure on the category of localized transportable morphisms can be pulled back to the category of DHR BF representation. So tensor products, conjugates, all that jazz. Another thing you might be wondering is, again, we typically think of charges as being associated with the action of some gauge group. The charges are sort of Casimir invariants of the gauge group. It also turns out that this category is dual in a kind of precise sense to the category of representations of a compact gauge group. So at the heart of this chunk of algebraic quantum field theory that's been sort of worked on by Doppler, Haag, Roberts, Buchholz, and Friedenhagen in various stages, you get this thing, which I will only gesture at in sort of in very general terms. The basic idea is starting with the category of representations that satisfy these boundary conditions. I can then naturally reconstruct a big Hilbert space with an algebra of something that looked like fields in Whiteman field theory loosely, and a compact gauge group such that the algebra of observables ends up being the fixed point algebra or the fixed point subalgebra of F under the action of G. And if I take my big Hilbert space, the action of G decomposes this thing into different superselection sectors that transform in a particular way under the gauge group. And those are going to be direct sums of DHR BF representations. So there's a direct one-to-one correspondence between representations that satisfy these boundary conditions and strongly continuous unitary representations of a given compact gauge group. So I can start with all of this gauge invariant algebraic stuff, and if I want, reconstruct a kind of minimal field system that has a gauge group acting on it. So I can recover something that looks like a more traditional picture of charges from all of this. Okay. One more technical idea to sort of keep track of in what's to follow. Pretty much all proofs of the algebraic CPT and spin statistics theorem at some point connect to this old theorem from constructive quantum field theory. So Bijan and Wickman, back in the, I want to say early 70s, proved that in models of the Whiteman axioms, and then in the vacuum sector, the algebras that are, of the field algebras that are associated with space-like cones, or that's not space, sorry, space-like wedges, here's a space-like wedge nestled on the side of a light cone, have really interesting geometric properties. So in particular, these algebras have certain special invariants that we're going to get to see in gory detail in a second. One of these invariants, the modular automorphism group, ends up generating wedge-preserving Lorentz boosts. And the other modular invariant, the modular conjugation operator, generates a reflection of the wedge onto the opposite wedge, which looks like a P1T reflection. So it reverses time and reverses one direction in space. Now this theorem relies on ingredients from Whiteman field theory that we don't have in algebraic quantum field theory, at least when we start in the framework that we've started in. But there's all sorts of arguments to the effect that we expect this property to follow from more basic algebraic assumptions about the observables. So here's a technical property, which we're going to try to prove en route to the spin statistics and Cpt theorem in most tellings of it. So the property is going to be that in the vacuum representation for any space-like wedge, the wedge modular unitaries that are associated with the observable algebras assigned to wedges generate the unique group of wedge-preserving Lorentz boosts. And then that's going to be used as an ingredient in the rest of the theorem. It's worth pointing out that a lot of discussions of the CPT and spin statistics theorem sort of start with this, and they'll say, we've got this really interesting geometric property for vacuum wedge algebras in constructive field theory. How could we secure those same technical properties in AQFT? One of the things that's difficult here is that it's sort of not at all obvious sort of what's the physical motivation for that, or what these particular modular invariants are sort of what their role in the theory is. And so by starting back at the Hogg-Kossler axioms, we're going to try to kind of piece together what physical justification there might be for this starting point. But again, we're not going to assume the Bijan-Wickman property. We're going to try to prove it en route. OK, so preamble done. We're going to walk through the algebraic CPT theorem, starting from the Hogg-Kossler axioms, and try to motivate kind of each step. And then we're going to step back and kind of, at the end of all this, there'll be some nice maps of how the logic is supposed to work, and then we'll look at what might be happening in the CPT or in the spin statistics theorem. So as I said earlier, the Hogg-Kossler axioms require covariance under connected Poincare transformations, right? Translations, boosts, and rotations. Maybe under maybe under the universal cover of the connected component, but there's no reflections here, right? So it's not at all obvious where any sort of reflection symmetries might enter into the framework, right? So if we're coming to algebraic quantum field theory from Lagrangian field theory and thinking, well, we've got good reason to think that there's a kind of general CPT symmetry hiding somewhere in any well-behaved relativistic QFT. First question is, well, where could it be in the algebraic framework? Because there's nothing obviously about reflection symmetries in the sort of stated initial assumptions. So our first observation is actually there's a kind of reflection symmetry hiding in plain sight. Every single C-star algebra used by the theory has a canonical involution defined on it. Here is properties. Essentially, what we should think about is something like this, right? So the C-star algebra has a bunch of self-adjoint operators that we think are the operators that represent physical quantities. Then there are all these non-self-adjoint operators. Any operator in the algebra can be sort of written in complex form, h plus or minus ik, where h and k are both self-adjoint operators. And this involution is going to act as complex conjugation, sending h plus ik to h minus ik. So broad picture, you can think of a C-star algebra as kind of like the complex numbers. There's a real line that's the self-adjoint subspace. And then there's this sort of canonical conjugation operation which reflects the algebra around that self-adjoint subspace. So technically, it's not an automorphism of the algebra because it reverses the order of the product here, and it acts conjugate linear on the identity. So there's a complex identity element I. It maps I to minus I. So it's strictly speaking not an automorphism, but it fixes the self-adjoint subspace. And if you think the self-adjoint subspace, those are the observable operators. Those are the things that represent quantities. Then we might treat this kind of involution as a sort of more generalized symmetry. And there's sort of a way of making this precise. I could start with the same underlying real vector space, the same norm, and I can equip that with either one operator product, A, B, or the opposite operator product, which is equivalent to BA. And I can also add either the complex unit I or the complex unit minus I. And when I do that, I can get different sorts of algebras that are naturally related to the original algebra. So this guy has minus I as the complex unit and the opposite product. This guy has just the opposite product, the same complex unit. This guy has minus I as a complex unit, but the same product. And what you can prove is that every C-star algebra is naturally isomorphic to its conjugate opposite algebra. It's anti-isomorphic to the opposite in the conjugate algebra, and conjugate isomorphic to the opposite and the conjugate algebra. These two guys are naturally isomorphic. Okay, some interesting math. Is there any physical significance of this involution operation and the various natural isomorphisms between a C-star algebra and its opposite? So our second important observation is the following. If any of you have seen a talk by me before, you know this equation appears at some point in the talk, no matter what happens. Right, so this sort of gets at the question of why do we use C-star algebras in physics? In a non-commutative C-star algebra, you can take the operator product and you can naturally decompose it, and the natural decomposition is given by the involution structure. You can naturally decompose it into two different products. This guy, which is a non-associative Jordan product. This guy is going to encode all the spectral information about observables. And then this guy is an associative non-commutative Lie product, which encodes the way in which observables generate symmetries in the theory. Right, so going back to the original idea of C-star algebras like the complex numbers, well, if we think that the observables, the physical quantities, are the self-adjoint subspace, what are all the other operators doing in there? This, I think, gives a kind of glimpse at what those things, a kind of general story about what those things might be doing. The non-self-adjoint elements are related to this thing here. They're related to the way in which every self-adjoint operator can generate some symmetry of the algebra. Combining this observation with stuff on the previous slide, we've got this sort of nice taxonomy of what's going on here. Remember, we had the original algebra. Here's our C-star product. Here's our complex unit. The conjugate opposite algebra has the opposite product, the opposite complex unit. These guys are defined similarly. For our purposes here, the important thing to note is that actually the original algebra and its conjugate opposite have the same Lie product. They have the same generating relation between symmetries and observables, whereas the opposite algebra and the conjugate algebra have the opposite Lie product. They have these sort of exact opposite generating relation between symmetries and observables. You can see what's going on here really elegantly by sort of switching and instead of looking at the C-star algebra, look at its state space. Right, so remember, characterize the states as linear functionals on the algebra. These guys form an interesting convex set with really cool geometry. Here's the kind of, the core idea here. The Jordan product is essentially dual to the convex geometry of state space. So in particular, the faces of this convex set form a lattice, and that lattice looks like the lattice of projection operators that encode spectral information over in the C-star algebra. And then the Lie product ends up being a kind of global orientation of this state space. It's literally a way of assigning which operators generate which symmetries. So here's a really simple example. This is the state space for a two-level quantum system. Each self-adjoint operator, A, is going to pick out a pair of antipodal points, max A and min A. And then these non-self-adjoint operators, IA and minus IA, are going to generate rotations of the state space around the axis that spans these 2 points. And essentially the choice of orientation is, does IA generate rotations that way or that way? So this has whatever you want to call this, clockwise orientation or something like that. You can show that global orientation, this is a very simple example, but you generalize this to really, really complex state spaces, this still holds. There's a nice one-to-one correspondence between Lie products on the C-star algebra and global orientations on the corresponding state space. So this helps capture the idea that what's going on back here is that this guy is encoding the spectral information. This is the complex geometry of the state space, and this guy is encoding the generating information. Okay, so what we have now is this picture where we've got, for every C-star algebra, there's this involution, and the involution structure is going to be related to all of these mappings that map algebras onto its opposite, so algebras that have opposite orientations or opposite generating relations between symmetries and observables. Right, so now, again, we're eyeing physics here, and we're thinking, okay, so I've got this thing that looks kind of like a reflection symmetry. Could this reflection symmetry be related to CPT in any sense? And there's a couple of sort of significant constraints. For one thing, at least there's an interesting question about whether or not CPT can be spontaneously broken in the vacuum sector, but at least in many models of physical interest, it isn't. The vacuum state's left invariant by CPT symmetry, which means that if the star operator is somehow related to CPT, at least in many models, it should be implementable by some unitary or anti-unitary operator in the vacuum representation. So we can ask this motivates this general question: can star be implemented in the vacuum representation for some arbitrary C-star algebra and some arbitrary model of AQFT? In general, no. But because of the Riesz-Leiter theorem that we met earlier in this morning's talk, it turns out that there's a sense in which a piece of it always can be. Right, so the Riesz-Leiter theorem, which physically we might think of as characterizing the sort of influence of really long range vacuum correlations in AQFT, tells us that the vacuum state is cyclic and separating for every local algebra in the vacuum sector. Sorry, every local algebra in the vacuum sector generalizes, but we only need the vacuum sector here. So what that means is we can take this map where here capital omega is the vector that implements the vacuum state in the vacuum GNS representation. So we can take this map and show that it defines a closed operator S that implements this transition from A to A star. S won't be unitary or anti-unitary in general, but it's got a polar decomposition. And one piece of the polar decomposition, J, is always going to be anti-unitary. So the moral here is because of really long wavelengths or long wavelength correlations in the vacuum sector, part of the star operation acting on the Hilbert space can be represented by an anti-unitary operator, right? It's the first part of the polar decomposition. So this is a huge technical subject. It's called Tomita-Takasaki modular theory. It's the study of these guys. These are the modular invariants that I mentioned earlier. So the modular invariants are the parts of the polar decomposition of the operator representing the canonical involution in a situation where you have a cyclic and separating vector. For our purposes, the two most important things are these two. This is a strongly continuous group of unitaries. It leaves the algebra invariant. The modular conjugation is going to map a local algebra onto its commutant. And if you think back to microcausality, we know that space-like separated algebras commute, so this is going to start to look like possibly some kind of spatial rotation or spatial reflection. Okay, so a couple of more observations about this guy. Since J is anti-unitary, it reverses the Lie product. So it's going to be a symmetry that ends up reversing the generating relationship between observables and symmetries. So in particular, suppose we have, here's the Heisenberg dynamic, so we've got some automorphism that's supposed to be our time translations. That can be represented in this fashion, where P0 is the generator of time-like translations in some Lorentz frame. If it turns out that J commutes with P0, commutes with our Hamiltonian, then you can prove that this sort of follows by an elementary algebraic argument that this is going to map the dynamics to its sort of reverse dynamics. So the question is, does it? Does J commute with the translations? Second observation here. I don't know what I just clicked up there. Maybe that will go away in a bit. As I said before, since J is a modular conjugation, it maps a local algebra onto its commutant. This prompts the following sort of question. So are there any sort of regions O where O is isometric to its space-like complement and where we expect duality to hold? Because if that were the case, then this would start to look really like a reflection symmetry, because it's going to map the algebra onto its commutant. If those are associated with regions that have the same kind of spatiotemporal structure, this is going to look like a reflection. I don't know how to get rid of that. So here's an interesting little lemma. It turns out that there are regions like this, space-like wedges, and they're sort of essentially the only causally well-behaved regions in Minkowski spacetime like this. So if O is an open, convex, causally complete proper subregion in Minkowski spacetime, such that O is isometric to O prime, then O is a space-like wedge. So that's sort of one sort of interesting bit of physical motivation for why wedge regions are interesting. Moreover, on that sort of tower of duality conditions, we've seen that wedge duality is weaker than Hogg duality, so we might expect it to hold in a wider range of models than Hogg duality, but it still entails essential duality, so it's going to give us the ingredients we need to talk about DHR and spin and statistics and all that good stuff. Okay, so that's sort of the physical motivation. At this point, now there's a whole bunch of analytic continuation arguments that I'm not going to go into in super detail. What's important for our purposes is the sort of logical structure here. So the first thing you can prove is that just starting from the Hogg-Kossler axioms and weak additivity, you can prove that the modular unitaries and the modular conjugation have the right commutation relations with the translations, right? So here U of A is some unitary operator that's representing the translations in the vacuum sector. So right, this is saying is that the action of the modular automorphism group maps U of A to U of, and then here's your wedge preserving Lorentz boost applied to that translation. And the action of J is going to take you from U of A to R of A, where R is just P1T reflection. So take a translation in this direction, then P1T reflected according around the edge of the wedge. Right, so that immediately tells you all sorts of interesting things. It commutes with the dynamics, so it answers that earlier question. That's going to end up preserving particle spectra because that's all encoded in the representation of the translations. And it's got the correct translations, correct commutation relations with the translations to be interpreted as a P1T reflection, or at least the J operator does. Probably take 10 and then, yeah. And now it turns out that this is enough to give you the Cpt theorem in low dimensions. So in 2 dimensions, you're done, which is pretty cool. Well, you're not done, but you can get to where you need to go from here. In higher dimensions, though, this is not enough. And basically what you can show is that even though this is going to essentially reflect, like if you slice a wedge and you get your triangle cross-section, it's going to reflect that. It can act non-geometrically along the edge of the wedge. And so you need these additional analyticity assumptions that guarantee that it acts geometrically along the edge of the wedge. So there are two really technical assumptions here. Since we're low on time, I'm probably not going to go into them in gory detail. The punchline, though, is that you make these technical assumptions, these analyticity assumptions. And the first one, B analyticity, is going to be equivalent to wedge duality. So to the claim that the algebra you assign to the space-like commutant of the wedge is the commutant of the local wedge algebra. And the Biesignano-Vikman property, namely the property that the modular unitaries generate the wedge-preserving Lorentz boosts, that's going to be equivalent to the second additional assumption, the B reality assumption. These are not standard names. I've called them B analyticity and B reality because they come from the work of Borchers. So that's if you ask a physicist about B reality, they're not going to know what you're talking about. Okay, so at this stage, what we can do is, once we've got the idea that the modular unitaries associated with the wedge in the vacuum act as wedge-preserving Lorentz boosts, we can define a representation of the Poincare group by setting the wedge-preserving boosts equal to these, defining them as the action of these modular unitaries. This is usually called the minimal representation, and one of the cool things about the minimal representation is it's got reflection symmetries, because the delta operator has all sorts of really nice analyticity properties. It satisfies the KMS condition. So if you've got the vacuum state restricted to a region, say the wedge, the vacuum state looks like a thermal state in that region, and that can be encoded in a certain set of nice analyticity properties for the modular automorphism group. Since it's also the modular automorphism group is also related to the J operator, since they're the polar decomposition of the same Tomita operator, the S operator, what you can show then essentially is that J is going to be equal to the product of this thing, which is the analytic continuation of this guy, and this is well defined, and it looks like a complex Lorentz transformation. And your non-unitary operator implementing your star symmetry. So you use these properties to prove that actually, if you combine your P1, so first of all, you prove that this guy implements a P1T reflection, then you combine it with a rotation by pi in the characteristic 2 plane of the wedge, and then that gives you a CPT operator acting on your net of algebra. So you've got now a proof that there's a CPT operator here. The problem at this stage is that you don't know that this representation is the same representation you started with. You've got some representation that's posited by the covariance axiom. You don't know that these two things line up. But if the distal split property holds, there can only be one representation, and these things align. So that's another important ingredient in the proof. Is that all? No. It turns out it also conjugates charge. Why it conjugates charge is super interesting. Essentially, the reason is that because we've got an operator that's implementing a uniform reflection on spacetime, it preserves the kinds of regions that the charge morphisms can be localized in. So it preserves double cones, it preserves space-like cones. And remember, it's flipping the Lie product. So it's flipping the generating relation between symmetries and observables, which include, in this case, both external spacetime symmetries and internal symmetries, gauge symmetries. So this is going to map a charge morphism onto its conjugate. I'll skip over the sort of more gory explanation of that. So here's the map we just came up with at the end. We start with the Hogg-Kossler axioms plus weak additivity. That gives us the Reich-Schlieder property, the existence of modular invariants, as well as the nice commutation relations for these modular invariants of the wedge and the vacuum sector. We add B analyticity that allows us to prove wedge duality. We add B reality, and there's one other slight technical property that I glossed over. It's not super important. That gives us the Bézier-Wickman property. We add the distal split property. That allows us to argue that the representation generated by the modular invariants is equal to our original representation. And then meanwhile, back at the ranch, we've been developing the entire DHR BF picture, which allows us to talk about charge conjugation, et cetera. And then combining those two ingredients, we get the argument that this thing actually implements a CPT reflection. So that's pretty cool. Now, one question is, where does the spin statistics theorem fit in here? And it turns out that once you have a CPT operator, there's a kind of very quick natural argument that gets you the spin statistics connection. So go back to the original chicken and egg problem. There's the question of which one comes first. Obviously, the egg comes first. So in this kind of map of the logic, the spin statistics connection ends up being the chicken. You can see these sorts of arguments at play in the kind of original four-dimensional proof of the spin statistics theorem by Guido and Longo, as well as a kind of follow-up paper by Kuckert. Let me explain this slide, and then I'll sum up. So one question is, where do statistics arise in all of this? Well, if you go back to the DHR picture, you've got a rule for composing charge morphisms. And if the charge morphisms are localized in space-like regions, they end up commuting. And so if I hit the vacuum state with n copies of the same charge morphism, and these guys are all, if they're not space-like separated, I can transport them to space-like separated regions, and that's going to be unitarily equivalent. This gives me a way to define a kind of tensor product structure on charge states. And of course, if these guys are space-like separated, the order that I hit the vacuum state doesn't matter. However, the vector that represents this tensor product state in a given Hilbert space will change if I permute the order that I apply the morphisms. So this gives rise to an action of the permutation group in each sector. Enter the representation theory of the permutation group. You can characterize these representations by some parameter plus or minus 1 over d, where this is a natural number. The plus 1 over d case is going to give you bosonic statistics and parabosonic statistics. And the minus 1 over d case are going to give you fermionic statistics and parafermionic statistics. The 0 case is a kind of weird infinite case, which is ruled out by the split property in our framework. So then what you show is that we just argue you have the CPT symmetry on the observable algebra. You appeal to the Doppler-Roberts reconstruction theorem, that big theorem from way back at the beginning that says you can reconstruct a field algebra, and show that the CPT symmetry extends to that. The only difference here is that rather than satisfying duality for wedges, it's going to satisfy this thing called twisted wedge duality, because space-like separated fermionic field operators can anti-commute. And so that this twist operator describes that as defined with respect to the statistics parameter for the given sector. And then the punchline is you want to show that rotating by 2 pi is equivalent to, or returns the identity plus the sign of the relevant statistics parameter. And the argument here is kind of elegant and geometric and pretty cool. If you imagine you start in one space-like wedge, there's sort of 2 ways to get to the other wedge, the opposite wedge, right? You can either use your modular conjugation operators to reflect it, or you can rotate it by pi. Then to get back, you can either continue the rotation by another factor of pi, or you can use the modular conjugation here and reflect it back. In the observable algebra, those are both the identity. And you know they're both the identity because there's only one representation of the Poincare group on the net because of the split property. When you're working with the field algebra, though, there's this twist factor. And what you can prove is that when you rotate around by 2 or reflect back, you're going to get a sign associated with the statistics as a result. And so that proves that the 2π rotation gives you back the identity multiplied by the sign of the statistics parameter. So that's a really simple algebraic argument. We could also try going back to the very beginning and sort of seeing if we could tease out simpler, weaker properties that gives us a spin statistic connection. And there's one potential strategy to do that where you impose the assumption of a mass gap, and that's kind of the critical point. There's an alternative argument that works like that, but I think we've run out of time, so I'll skip over that. Here are a couple of big open questions that I want to leave you guys with. In all of this, right, we needed some kind of duality to get the DHR BF picture off the ground. And there's an interesting question with what explains that. Because on the sort of the way that I was telling the story, you first prove wedge duality, then you use that to get the CPT and eventually the spin statistics theorem. But there might be an alternative strategy where you start with weaker properties, get essential duality, get something like the spin statistics theorem, and then eventually prove the Bayesian-Wickman property in CPT coming from that. And so to figure out what the right explanatory order is, I think one of the things we have to figure out is what's the right explanation for these duality properties. There's some other technical things, but I realize I skipped over that slide, so I can't ask that question. One final thing I'll say is that there's this big kind of explanatory black box, right? What explains wedge duality? It seems like you need additional analyticity properties to prove those. But there's this sort of open conjecture that you can get those analyticity properties for free from the Hogg-Kossler axioms, weak additivity, and the split property. So we don't have any, we have counterexamples to the Bayesian-Wickman property that violate one of these three things, but we don't have any that satisfy all three. And there's various arguments that the three of these things together should give you this. And so that might give you something like a better physical explanation for where the Bayesian-Wickman property comes from. OK, I think I've overloaded you guys at this point, so we'll go to questions and loop back. Thanks.
Okay, so if you have a question, please raise your hand and keep it raised high until I acknowledge you. Yeah, we'll start with Josh.
Yeah, so I guess, are you willing to make a full conjecture as to which explains which? Like, if you have the debt, would you think that one of them is explanatorily prior to that they're on the same footing?
Yeah, I was building towards that, and then, I'm glad you asked this question first. So if you do this other strategy and try to go back and say, forget this side of the argument, just try to get the spin statistics connection from the weakest properties you can think of. One of the things that happen is that once you have the spin statistics connection, you can then add something else. You can add an asymptotic completeness assumption. Because essentially the way this argument is going to go is you restrict everything gets restricted to the one particle subspace in each sector. And you can show that there's all sorts of nice analyticity properties there. And that's enough to get you the spin statistics connection. But then you need asymptotic completeness to show that that then gives you something like CPT across the entire Hilbert space. And that doesn't seem to play a role in the argument to get you to here, which is interesting. But then the other thing that's weird is that to actually get from here to here, what you end up doing is essentially proving either CPT or something slightly weaker like crossing symmetry on the one particle Hilbert space, along with the Bayesian-Wickman property on the one particle Hilbert space. So this thing looks like a kind of like one particle Hilbert space version of what's going on over here ultimately. So if you kind of read the logic at face value, it seems like this is the structure. So now the Bayesian-Wickman property in CPT is the chicken. But it feels a bit explanatorily weird because it seems like the argument that you used over here to get that has been sort of reproduced on the one particle Hilbert space over here, more or less. I think my hope is that you can get the Bayesian-Wickman property from the things I just mentioned, from the split property plus this stuff, and then the logic would look something more like this, where these things, which are much more in the sort of natural physical assumptions, give you the Bayesian-Wickman property. And then there's an interesting question, which is, from this, do you get kind of one argument to CPT and then a sort of slightly different argument to spin statistics, or is it the original thing where once you get here, then you just immediately get to here. And that's, I think, an interesting open question. So there might be two chickens, in other words, that kind of emerge from a common underlying explanation. And, you know, I'm not super confident, but given what I've seen so far, I think this is probably more like what's really going on. For one thing, I think this is the structure of this argument is going to generalize to like curved space and low dimensions easier than the structures of the other arguments. So that's another reason to think that this might be what's going on. Yeah.
Same kind of question as Josh's. A slide went by with words like mathematically weaker or explanatory.
Yeah. The philosophical slides. Yeah. Yeah. Okay. So one of the things that makes this project really complicated is that you might just say, oh, just find the mathematically weaker assumptions, and that'll tell you what the explanatory structure is. But actually, in many cases, mathematically stronger assumptions are the ones that end up having some natural physical motivation, and they have a bunch of consequences, so that thing explains the weaker ones. So one thing we want to be careful of is assuming that, oh, well, the mathematically weaker assumptions are obviously the explanatorily prior assumptions. In fact, I think in many cases, probably the opposite. The other thing is that this is a bit messier point. I don't think that explanatorily prior and metaphysically prior always line up, right? So you might have a story according to which, you know, if you go back and look at like, there are all these properties of models of AQFT here, right? You know, the fact that the model has, you know, finite statistics and DHR charges. What explains that? We might have some kind of metaphysical story where that's grounded in some very basic facts about the dynamics or quantities or something. But insofar as what we're interested in here is something like, we think that all models of AQFT have some, or suitably well behaved, have some structure in common. Why is it in virtue of that structure that we have these properties? It would be a kind of explanatory mistake to dive all the way down to like the details of some specific dynamical model and explain it up that way. So, I mean, another way to think about it is that we're kind of, it may be the case that we do want to do that, but I don't want to, you know, I don't want to necessarily conflate those questions. Yeah. So like I have a version of this talk somewhere, and someone was asking me, like, they had a view where there's a clear logic because certain things were more fundamental than the others. And I mean fundamental like the dynamics explains everything fundamental. And the thought there is that you can still have that picture, but that may not be the right explanation for why all of these models have something in common. And that sort of depends on relations between the emergent structure as opposed to what they think is fundamental. Yeah. This sort of ties into the things, the previous question. Yeah.
Ben?
Yeah, so I guess I sort of want to ask a question about the title of the talk. Because, okay, so the title was Cpt spin statistics, figuring out the bottom of the statistics error, but it's
And state-space geometry. Yeah.
Okay, so I see the connection between state-space geometry and CPT, you know, like vaguely written here, but
Yeah.
But I can see it.
You have a better idea for some reason. I don't want. Yeah.
But what's the connection between the state-space geometry and spin statistics?
Yeah, good. No, that's so. I mean, there's a reason why the first part of the talk was way more detailed than the second part, because the first part has been turned into a paper, and the second part is in the process of being turned into a paper. You know, eventually, I'd like to find some nice connection between the state-space geometry stuff. And right now, all we have is, I mean, on the first way of telling the story, right, like this, we have this sort of, there is a kind of connection here, right, where we've got the, you know, this whole story is the story of the implementation of a particular algebraic star symmetry, right? And then at the very end, there's this interesting, like, that story jumps over to the field algebra because of the DR reconstruction theorem. And then there's this really quick algebraic argument at the very end. And so one possibility is there's some nice story about what's going on there. And it would be great if you could tell that story without using the DR reconstruction theorem, because then you wouldn't have to use the field algebra. You could just appeal to the sector structure. So here's another way of putting that. Good. I mean, I went through this really fast, but in the DHR picture, you have conjugate charge sectors. And there's some sense in which the relations between those conjugate charge sectors are encoded in the intertwining operators between them. And there's a well-defined way where if you use the adjoint action of your wedge modular conjugations, you flip all of that structure. And so you map from one charge sector to its conjugate. So as we're, the punchline is the relational difference between a charge sector and its conjugate is somehow coded up in the direction of arrows in the category, and acting with the CPT operator flips those arrows. If you've got fermionic statistics, that gives rise to a kind of super selection rule too, right? So like, for example, if you take like the representations of the canonical anti-commutation relations, there'll be a bosonic sector that's the vacuum sector and things like the vacuum sector that transforms as though it were like a bosonic state. And there's like the one fermion sector and the things equivalent to it will transform like a fermionic state. So when you have fermionic degrees of freedom in your theory, you're going to get natural super selection rules that come from that. And the thought is that essentially what the spin statistics theorem is saying is that that super selection structure too, just like the charge structure, is also going to be capturable by these arrows in the DHR category. And so flipping those things is going to be a nice sort of reflection symmetry there. You can make it a little bit more precise too, because actually there's an operator, the Bose-Fermi operator, that it's the mysterious kappa that's sitting in. It's the definition of. Sorry. Right. So in the definition of the twist operator, there's this k here, and k is actually an element of the center of the gauge group. So this is another fancy way of saying. So remember, I said you've got this gauge group. Well, that actually already encodes information about the statistics, because it's essentially in DHR language, the gauge group is just like code for all of the symmetries that leave the algebra invariant, which include this Bose-Fermi symmetry. And so again, this is very loose at this point, but the thought is that insofar as you already have a kind of story about how the action of the modular conjugation is going to flip the arrows and so flip conjugate sectors onto their partners. It's going to do the same thing with the relations between these bosonic and fermi, or it's going to act as the twist on the fermionic sectors, I think is a better way of putting it. There's another connection, but the other connection is much harder to see. In the version of the spin statistics theorem where you go up this side of the tree and work with the one particle Hilbert space, the way that proof actually works is you show that there's a kind of geometric Tomita operator S that acts on the one particle Hilbert space, and you show that that thing has the Biesiano-Wickman property. So in the more complicated sort of one particle versions of the spin statistics theorem over here, there's a kind of trace of the logic over here. And I'd love to have a better understanding of how that works. It's really, really hard to grok. So that's another potential connection.
Other questions? I'll insert myself. So at the beginning, did I catch you right? You said that there's issues with massless particles?
Yeah, so the
Can you just elaborate on that?
entire DHR-BF picture does not apply to massless theories.
I see.
It's what's interesting. So okay, yeah, good. So that was a good question. So in theories with a mass gap, right? So where there's no massless particles and you've got an isolated eigen space for the first mass parameter. What you can show is that representations that are Poincare covariant satisfy the spectrum condition are one-to-one with BF representations. So one-to-one with representations of the algebra that are equivalent to the vacuum outside of some space like cone. That's the core of the Buchholz-Friedenhagen analysis of topological charges. Now, what's weird is that actually, it doesn't matter which space-like cone. All that matters is there's a topological obstruction at infinity, so the direction of the cone doesn't matter. What you can show is that in theories like quantum electrodynamics, where there's massless particles now, as long as none of the massless particles are charged, charge states will still be localized in some space-like cone, but now the direction matters. And essentially, the direction of the cone is associated with soft photon polarization clouds. And so that actually gives rise to another super-selected quantity. So the sectors in QED are going to be labeled by global charge and the direction of the polarization cloud. And the problem is the direction, that's a continuous quantity. And so you've got, rather than a discrete set of parameters for labeling your super-selection sectors, you've got a continuum. And so showing that you have like nice categorical properties for the associated set of morphisms is like, we can't do that right now. But what we can do is we can say, well, forget the polarization clouds, just quotient out by all the representations that have the same charge. And you get these things called charge classes, and then you can do a certain amount of work with that. So the last time I checked, Buchholz and Roberts had proven that in the charge class picture, you can get particle-antiparticle symmetry. So you can get that there's, for every particle, there's an antiparticle with the same mass and spin. But I don't think they can get all the way from that to full-blown CPT and spin statistics. But, I mean, that's a couple of years old now, so maybe it's, I don't know, I haven't checked yet. Yeah.
Other questions? No? We've got one more. So, and I don't know how central this is, but at one stage, you mentioned that you're relying on some properties of the Whiteman, models of the Whiteman axiom.
Oh, yeah.
And I just, can you help me fill in the story of how much that matters? And I know there's somewhat restrictive circumstances under which you can prove recovery results between Kastler and Whiteman, but I don't know how that fits in your story.
So this has a short answer. The answer is I'm not actually assuming anything about Whiteman. So the whole framework, the ones, I think the confusing slide was back in the day, what the Bayesian-Wigman property, you can just prove from the Whiteman axioms. And so the idea is we can't prove it because we don't have the Whiteman axioms. But we can say, well, what else, what constraints on the algebras would allow us to get the Bayesian-Wigman property? And that's the nasty slide with all the analytic continuation. These are like two technical analytic properties that you could add to what you already got in the Hogg-Kastler framework that would give you the Bayesian-Wigman property. But you're not assuming anything about underlying. Now, one thing that is, so you do use the DR reconstruction theorem to get a field algebra. And so it's an algebra of observables that are gauge variants that look sort of like Whiteman operators, but they don't have the same localization properties, right? They're not smeared with nice test functions and that kind of stuff. So, a field algebra is sort of like you can get a field algebra from Whiteman theory in certain cases, but you probably know more about that than I do. But yeah, there's one theme in a lot of this, which is especially when you get to the spin statistics stage, like all the proofs that I know of use a field algebra at some point. So they rely on DR reconstruction. And they all say it should be possible and would be really nice if we didn't have to use this crutch. And so that's presumably something that would be, again, if you're interested in the explanatory structure, it would be helpful because then you could get at the spin statistics connection without using these, non-physical field operators. Yeah.
Anything else before we wrap up? If not, then let's thank Noel again. So we have